The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone, and welcome to the 2021 Virtual Viscosity Summit. We are going to give everyone just one more minute to sign on and make sure everyone's with us before we get started with our first presentation of the day. All right, we are going to go ahead and get started. Good morning, everyone. My name is Eden Reed, and I am the Senior Marketing Associate for Rheosense. I'd like to welcome you all to the 2021 Virtual Viscosity Summit. We're very excited for each of our speakers today and the expertise they'll be sharing. Before I introduce our first speakers, I would like to go through just a few housekeeping items. As you can see on the screen, here's our agenda, and please note that we do have a 1-hour lunch break from 12 p.m. to 1 p.m. Pacific time. We would love to connect with you all on social media, so please go ahead and follow Rheosense on LinkedIn, Facebook, and Twitter to help stay up to date with all the latest news and viscosity discoveries and updates. Each of our speakers has left time at the end of their presentation to answer questions, so we encourage you to please use the chat pane that you can see on your screen to ask your questions throughout the presentation, and then our speakers will be sure to answer them at the end. And finally, a reminder that all of our presentations today are being recorded, and the recordings will be sent out to all registrants 1 week after our event concludes. So if you miss anything, don't worry. There will be a recording sent out. Now, without further ado, it's my pleasure to introduce our first speakers, University of Texas at Austin Professor Dr. Keith Johnston and Graduate Research Assistant Amjad Choudhury. Keith Johnston received his PhD in chemical engineering from the University of Illinois. Over the last decade, his group, with Tom Truscott, has been developing an understanding of the structure and interactions of proteins at high concentration with a variety of techniques and models in order to design improved formulations to lower the viscosity and enhance protein stability. Amjad Choudhury is a graduate research assistant in the Makeda Department of Chemical Engineering at the University of Texas at Austin. His dissertation focuses on characterizing protein-protein interactions using small-angle X-ray scattering and molecular dynamics simulations. Today, they will be presenting interactions, clustering, and rheology of highly concentrated antibody solutions. And now I'll be turning it over to Amjad. Dr. Johnston, I think you may be muted.
Okay, I would Amjad, I would like to greet you today. Let me say a few words, and I'm going to turn it over to you. Amjad is very far along in his graduate studies. He has presented at meetings, at ACS meetings, and other places on his work on these protein colloids. Protein colloids are the most complicated colloids that we study because of the fact that you have the topology of the molecular level on the surface, and so it becomes very important, as you know, to control the rheological properties for formulation, subcutaneous injection, processing, even monoclonal antibody discovery. And so for over a decade now with Professor Tom Truscott, we've been very interested in understanding how viscosity relates to interactions between proteins. And we've used techniques such as DLS, small angle X-ray scattering. We probably find that what tells us the most about an interaction between proteins is the viscosity itself. And I think that what you're going to see now is a lot of progress in understanding how viscosity relates to the strength of the protein-protein interactions in concentrated antibody solutions. So if, I don't know how this is controlled, if we could go to the next slide. Okay, so let me cover a few of the earlier slides, and I really want to turn it over to Amjad, who has led this work. As you all know, a large number of high money-making pharmaceuticals are monoclonal antibodies. The recent ones of Lilly and Regeneron are what could really help us with this massive number of hospital patients with COVID and people dying of COVID, because if we could get these mAbs into people early on in the disease, as we did with our former president of the United States, it could keep these symptoms from developing and some of these unwanted needs. So there are just many cases where monoclonal antibodies are of great interest. Humira, you can see, is kind of at the top of the list, and the real key is, if you could do this subcutaneously, I think many people would be getting injections of these Regeneron and Lilly mAbs and not getting as sick. And so this could have an enormous effect on the economics and health of our country. What you find in these antibodies, they're used in many different kinds of disease states. And the goal is to be able to move from IV infusion. And this is what's really kept people from getting treatment for COVID-19. It's just too much trouble to get the IV infusion of these mAbs. And so unfortunately, we just don't have enough people that are getting treated, and thereby keeping people out of these hospitals. But hopefully this will get a lot better soon. If you could come up with subcutaneous forms of some of these therapies, it could be very desirable in the future. Next slide, please. And so I think what I'd like to do is turn this over to Amjad Choudhury. He did his BS at Ohio State, and he's been very active in both rheological studies. He's done a lot to bring small angle X-ray scattering to play here. We've built a lot on interactions we've had for many years with places like AbbVie and Pfizer and Lilly and Merck. And so it's been very exciting for us to see what these companies could teach us about antibodies and some of their goals, and then to try to give some academic support to understanding rheological properties and interactions. So Amjad, would you like to take over?
Yeah, of course. Thank you, Dr. Johnston, for that great introduction to the problem statement in hand, and thank you everybody for attending. And so, as Dr. Johnston very clearly articulated, formulating these antibody therapeutics at high concentrations for subcutaneous delivery would be the ideal method for administering these drugs. However, the reason why this is not seen as commonly in the pharmaceutical industry is because formulating proteins at high concentrations can lead to certain challenges, namely issues with stability and issues with viscosity. And so here you see a schematic of what might happen when you bring these proteins very close together in a crowded solution. You may start seeing interactions occurring between these monomers of protein that can either lead to instability through unfolding and leading to larger clusters, or it can lead to sort of folded reversible oligomers that we believe play a significant role in viscosity and stability of these antibodies. So what we've established and what we believe is that these protein-protein interactions, or PPI, are what is responsible for a lot of the solution behavior that we see, and these comprise of short-range and isotropic interactions, such as electrostatic interactions. So that can include charge-charge, charge-dipole, hydrogen bonding, dipole-dipole interactions, but also interactions between hydrophobic patches that may be distributed unevenly on the surface of these proteins. And so because of this very high complexity of the surface and interactions between proteins, it is very difficult to predict the viscosity of these solutions at high concentrations from sort of standard, well-characterized low concentration measures of interaction, such as the second virial coefficient or KD, the diffusion coefficient you can get from DLS. And because of these interactions, the viscosity behavior is also not very well defined by standard sort of hard sphere laws of rules of viscosity, such as Einstein equations. And so people have gone in to try and understand what exactly determines the viscosity of these proteins. And there have been many studies, including some computational ones based on sequence, that have identified the components that may most contribute to viscosity are the charges on the specific domains of the antibody, specifically anisotropic charge distribution on the antibody, as well as the hydrophobic patches that can contribute to attractions that can lead to high viscosity. However, these models have shown very mixed success. Models using just this information from sequence have shown mixed success for predicting behavior, and we'd like to identify other properties directly at high concentrations using different techniques. Therefore, the objective of our study is to provide a mechanistic understanding of protein colloidal stability and viscosity, but not just at low concentration, but directly at high concentrations based on measurements of interactions and of understanding these reversible clusters that form in solution. We characterize these interactions in morphology by interpreting experimental data with coarse-grained molecular dynamic simulations. So currently, the state of the art is to develop these 12-bead coarse-grained models that can mimic the highly anisotropic shape of the antibody that can then be populated with bead-specific short-range attraction to mimic protein-protein interactions. And the experimental techniques that we will be focusing on, primarily small angle X-ray scattering. However, we've also used static light scattering in the past, and shear rheology is something that shows a lot of promise for the future. And once we have characterized our systems, we can relate the colloidal stability and viscosity to these protein interactions and cluster formation, specifically understanding the effect of antibody structure, pH, ionic strength, and cosolutes such as arginine to the high concentration colloidal stability and viscosity observed. And finally, with a greater mechanistic understanding of the viscosity and interactions in solution, we can see potential application for these models in predicting the viscosity during drug discovery or development stage, understanding viscosity behavior during protein processing, and also develop strategies for mitigating viscosity in highly viscous MAP solutions. So a little bit of background on the understanding of a relationship between clustering and viscosity. There have been many attempts to model protein viscosity and clustering using existing theories. So for example, people have tried to model protein clusters as chains of linear polymers, and then using rotation theory and entanglement to try and understand the viscosity. And they have shown that as you go higher and higher in concentration, you start to develop these sort of reversible linear chains that can reach, with multiple monomeric subunits and certain lengths that will then cause the increase in viscosity. People have further related this idea to shear rheology, where they have related the slope in the relative viscosity versus concentration graphs, breaks in the slope in the relative viscosity versus concentration to a critical concentration related to entanglement and reptation. And this has been shown to agree with shear rheology and relaxation times, further solidifying the importance of these reversible oligomers to the viscosity. And then finally, Ken Dill in New York has developed this thermodynamic theory based on the work time perturbation to show that the number of these anisotropic contacts in the molecule that can form these networks and these reversible oligomers determines how strong, how viscous the MABs can be. So for example, here, symmetric MABs, where you only have interactions between two fab arms, has an intermediate viscosity, whereas if you reduce the number of interactions just to one arm, you can decrease the viscosity. And if the FC arms, if all three arms of the MAB start to interact with each other, then that can significantly increase viscosity with the formation of networks. However, these models are not predictive, and we believe that using small angle X-ray scattering, we can determine the size and type of clusters, which we can then feed into these models and develop a predictive viscosity. Finally, in terms of viscosity mitigation and sort of tuning systems to get the most widest array of viscosity behavior, we have the concept of adding cosolutes to solution. And so what these do is these will directly inhibit interactions between these proteins, this PPI that we mentioned before, based on either charge binding or non-specific binding to the surface of proteins, and therefore reduce the PPI, break these clusters, and reduce viscosity. So for example, here we show some of our work where without any cosolutes, we get a certain viscosity. However, after adding certain viscosity reducing cosolutes, such as arginine, imidazole, or histidine, we can reduce the viscosity to below half what the original viscosity is. Further, people have done work on cosolutes, showing a wide variety of cosolutes that can reduce viscosity. However, there has been no way to predict whether a cosolute, what effect a given cosolute will have in an unknown MAB, just based on sequence or without measuring the viscosity. And so that's an active area of research while we're trying to understand what classes of MABs can fall into and how they'll respond to cosolutes. In terms of techniques, the most commonly used technique for one of the most commonly used techniques for measuring PPI in antibody solutions, both at low and high concentrations, is static light scattering, which at low concentration can give you the second virial coefficient, and high concentration can give you the S of Q, which is related to the compressibility and to net attractions in the solution. And so people have tried in the past to try and correlate viscosity to S of 0 to try and understand how PPI would affect viscosity. However, they've found that these correlations can be highly variable to not very strong. They can depend significantly on the identity of the MABs and are not generalizable across multiple MABs or ionic strengths. And so, therefore, a better technique is required, and we've shown good fits to viscosity using the cluster sizes that we've gotten from our small angle X-ray scattering studies. So moving on to an general introduction to small angle X-ray scattering. Basically, the idea is you're going to expose a sample to an incident beam and then collect the scatter plot in a 2D detector, which gives you a range of length scale at which the scattering occurs, and the length scale is determined is related to the wave number by this equation. And the scattering of a solution of antibodies depends on a number of different things. So the scattered intensity, I, is related to the volume fraction, the density difference in scattering, so the contrast of your protein versus your background solution. And then two components, the P of Q, the form factor, and the structure factor, where the form factor determines the shape of the particle that is leading to the scattering. And so at low concentration, where there are no interparticle interactions, the only contribution to scattering will be the form factor. And the structure factor, which encodes differences in scattering due to interparticle interactions. And so as you increase the concentration and you introduce PPI, the contribution and changes in scattering due to these proteins interacting will be encoded in the structure factor. And therefore, that is the parameter that is most interesting to us. However, interpretation of structure factors is highly complicated by the fact that the molecules we're studying aren't simple spheres with isotropic interactions, but are molecules with a complex shape and with a number of different anisotropic interactions on the surface. Therefore, to interpret this experimental structure factor data, we have also developed coarse-grained 12-bead models, such as one represented here. And this model, the shape of this model will mimic the approximate shape of an antibody, and we can controllably place interactions at specific sites on the antibody to try and mimic the protein-protein interactions that we'll see in solution. Once we have our model, we can run molecular dynamic simulations to get simulated SFQ and compare that with our experimental data to determine real space properties such as reversible clustering or viscosity. We are very fortunate to have a benchtop SAXS at the University of Texas, which lets us measure rapid high throughput in situ scattering for concentrations between 5 and 250 mg per mil, greater than 250 mg per mil in the minute time scale. And we can measure dynamics over hours or days. The instrument also lets us measure multiple temperatures. We can measure it in multiple solution conditions. And we have the capability in the future to develop this instrumentation further to measure small angle X-ray scattering under shear as well to compare directly to shear rheology data. On the front of simulations, as I've described already, we follow this general algorithm where we first optimize our coarse-grained 12-bead model to match the shape of the protein based on the form factor, experimental form factor, and then place specific intermolecular interactions on this model. We then run molecular dynamic simulations using LAMPS, which is just a software, and then interpret that molecular dynamics trajectory to calculate the simulated structure factor, which we will then compare to our experimental structure factor and then extract information such as the reversible cluster size distribution. This shows some of the intermolecular potentials that we're using. So as I mentioned earlier, the interactions that we're most interested in capturing are Coulombic interactions such as charge-charge repulsion or charge-charge attraction between oppositely charged beads, and also short-range anisotropic attraction such as dipole-dipole, hydrophobic interactions, hydrogen bonding interactions. And so we capture these in our model using 3 different interaction terms. The first is a simple van der Waals potential, which just gives a very short, weak attraction on all of the beads of the molecule, followed by an electrostatic potential, which adds a uniform charge on the molecule to simulate charge repulsion, especially in systems with low ionic strength. And then finally, on specific beads, so in these pictures, should the beads shown in gold, we will add an additional general Yukawa potential to mimic anisotropic bead-specific attraction. And we believe that it's these bead-specific attractions that lead to increased cluster size formation and leads to increased viscosity. So here we have a description of the experimental data and the fitting that we do. So on the far left, we have experimental SFQ data for a protein MAP2 at 125 milligrams per milliliter in 4 different solution conditions. So in purple, we have the condition with no additional cosolute. In green, we have the condition with 250 millimolar sodium chloride added to the sample. Blue shows 50 millimolar sodium chloride, and then finally red, instead of sodium chloride, we add 250 millimolar arginine. And first of all, we can see just from the experimental data that the different cosolute conditions significantly affect the behavior of the structure factor at low Q. And since Q is inversely related to the length scale, the low Q region corresponds to length scales that are larger than the monomer and where particle interactions will be most dominant. And so we can see that sodium chloride, which shows the S of Q at low Q, the highest S of Q at low Q, has the strongest relative attraction, and adding arginine, which is known to be a cosolute that reduces viscosity, significantly reduces that attraction. Finally, the lines represent our simulation, best fit simulations to the experimental data. And here we have simulations where the strength of the anisotropic attraction K is kept constant on all the beads. And what only changes in the simulation between the purple, the blue, and the green is the ionic strength that is modeled in the simulation. Since we believe that sodium chloride, that is the primary effect of sodium chloride in these solutions for this, that's the assumption for this system. And as you can see, with the same strength of attraction, we're able to get good fits to all three systems, which suggests that there is significant attraction present in the system, in these systems with sodium chloride on the order of 2.5 kBt. And then finally, to fit the red arginine curve, even accounting for the charge and the ionic strength, the only way we were able to fit the system is by reducing K to effectively 0, suggesting that adding arginine significantly reduces these anisotropic attractions. The advantage of doing these simulations is now we can go for, using these simulations, we can go directly to real space and study clusters directly. And so here we show the cumulative cluster size distribution, where the x-axis shows clusters of size n, and the y-axis shows the cumulative probability of finding such clusters in solution. And as you can see, for our sodium chloride systems, the clusters, you have significant numbers of dimers and larger order oligomers up to about size 10, whereas by adding arginine, we can reduce these the solution to a almost primarily monomeric solution, which we believe would have an effect, a beneficial effect on viscosity. And by the only way to get the sort of real space cluster distribution information is by fitting our SAXS data with molecular dynamic simulations. Here we have an example, in addition to the 4 systems that I showed earlier. Here we have an additional example of a very, what we like to call a misbehaving MAB. So we now have this additional MAB4 in sodium chloride, 250 millimolar sodium chloride system, which shows significant, very high viscosities, over 100 centipoise, even at 150 mg per mil. And we show that we can clearly distinguish between a very misbehaving high viscosity MAB and more appropriate well-behaving MABs by the significant upturn that is present in the S of Q at low Q. And furthermore, we are able to show what this upturn physically means by fitting our simulations to the S of Q, where this dark green curve in our cumulative cluster size distribution shows that, in contrast to the previous solutions, which had reversible oligomers up to about size 10, this highly attractive system and highly viscous system shows clustering up to reversible oligomers up to about size 1000, suggesting that there are these very long networks forming in solution, which can maybe system spanning networks forming in solution, which can lead to the very high viscosities that we observe. Another great benefit that we have discovered with our coarse-grained molecular dynamics simulations is we are able to fit across multiple protein concentrations using the same parameters without changing the parameters that feed into the model. So here we show for 3 different systems, 2 of them for one MAB, MAB2 in arginine and sodium chloride, and an additional one for MAB4. We're able to fit our experimental SFQ from 125 all the way up to 250 mg per mil with the same K, with the same strength of attraction as was fitted using the 125 mg per mil data only. And so the real promise that this shows us is we can then fit our model at a low protein concentration which is easy to get information on and is not material intensive, and then use those parameters to predict what the behavior is going to be at high concentration. And this will allow us to build predictive models that use low concentration experimental data and our coarse-grained molecular dynamics simulations to predict behavior at high concentration, behavior such as viscosity at high concentration, which is the system of interest. So we went ahead and did just that. We took our cluster size distributions that I've shown from our molecular dynamics simulations, and we fed it into the model that was developed by Ken Dill using Wertheim perturbation theory that I mentioned earlier, to try and see if our model is able to accurately capture the viscosity behavior across a wide range of systems. So this is the mathematical description of the model, where the viscosity is dependent on the concentration of the protein, the cluster size distribution, which we can obtain from SAXS, and this exponential function, which has two fitting parameters, which both Ken Dill and we showed can be generalized over multiple different proteins and also multiple different solution conditions. Therefore, with these two empirical fitting parameters, we are able to describe the viscosity behavior for these two systems, one with arginine, where the viscosity does not cross 100 centipoise, even above 250 mg per mil, versus another system with sodium chloride, where the viscosity is significantly above, reaches almost 300 centipoise. And in fact, we were also able to use the same model to accurately predict the viscosity of this highly viscous and clustered MAP4 solution as well. Furthermore, using this model, we can directly show the contribution of clusters of different sizes to the overall viscosity in solution. So here we plot this cluster contribution of the low viscosity MAP2 arginine system and the high viscosity MAP2 sodium chloride system. In the MAP2 arginine, even at 250 mg per mil, majority of the viscosity is being determined primarily by monomers and a small percentage of dimers, and very little contribution comes from larger order oligomers. However, as you change the cosolute and introduce a more viscous system, you see that, especially at high concentrations, the viscosity is primarily being determined by clusters greater than size 10, once again showing the importance of understanding and characterizing these reversible clusters in solution to understand the determinants of viscosity. And then finally, I wanted to close with looking towards the future and looking at the contribution that shear rheology can make to our understanding of interactions and clustering. So this is some data that actually Bardier collected while he was a PhD student in our group, where we show that systems with high viscosity, high initial viscosity, such as this system without any cosolute, will show shear thinning at a sufficiently high shear rate, whereas viscosity, when introduced to viscosity reducing cosolutes, not only reduce the initial viscosity, the zero shear viscosity, also eliminates the shear thinning behavior seen at high shear rates. And so the relaxation of these solutions can be related using existing theory to characteristic length scales of clusters and also characteristic rotation strengths. And we can use these to compare to our static measurements of interactions and clustering using SAXS to get an even better understanding of the types of clusters that are primarily responsible for the dynamical behavior that we see at high concentrations. And of course, the capillary viscometers that have been introduced by Rheosense are ideal for doing these shear studies on MAPs, especially using low solution amounts with the newer Initium instruments. So in conclusion, small angle X-ray scattering combined with coarse-grained molecular dynamic simulations offer a novel characterization tool for antibody protein-protein interactions at high concentration. which can play a significant role in mAb discovery, processing, formulation, or delivery stages of therapeutic antibody production. The strength and location of the short-range bead attractions, which represent the local anisotropic attractions present on the map surface, as well as the cluster size distribution and radial distribution functions, can be obtained by fitting our simulations to experimental SAXS data. This fitting routine has shown initial success in describing the structure factor over a wide range of concentrations from 125 mg per mil to over 250 mg per mil with a single K. And in the future, we would like to reduce the concentration that we need to measure to get a predictive measure of the protein-protein interactions in solution. Also, with information, with knowledge of the protein sequence, we can relate our attraction parameter K to the detailed sequence information in terms of charge, hydrophobicity, and cooperativity effects. And by reducing the concentration at which we can fit our K, and also making the K more representative of real solutions using the sequence, we should be able to use K to predict high concentration clustering and therefore viscosity. The information that we get from SAXS provides more information than other existing techniques such as static light scattering, dynamic light scattering, or NMR, and other techniques at low concentrations. As we have shown, we have already been able to show good good modeling capability of using our SAXS simulations and a viscosity model to predict viscosities from cluster size distributions, and we plan to validate that even further. And finally, shear rheology can be a complementary technique for characterizing cluster sizes and relaxation. With that, I'd like to end my talk by thanking my advisors, Dr. Johnston and Dr. Truscott, the postdoc that has been helping me with this project, Neha Manohar, and PhD students that have been my mentors and have led the project, especially Bart Deer and Jessica Hung, who were my direct mentors and have moved on to bright careers and presenting at seminars such as this. With that, I'd like to take any questions that you may have. Thank you.
Amjad, we do have a few questions that were dropped into our questions tab. And if anybody has questions now that Amjad's concluded, please still feel free to drop those in and we'll go ahead and start answering them. So Amjad, the first question is, do you ever have trouble getting low enough Q for structure factors studied using the benchtop SAXS as opposed to the synchrotron beam?
Yeah, that's a really good question. We have found that the benchtop SAXS is sufficient in getting a low enough Q to understand protein behavior in the systems that we studied. So right now, our benchmark is about 0.01 inverse angstroms, which correlates to hundreds of nanometers in terms of the length scale, which would correspond to multiple orders of multiple coordination lengths. And so we can see larger order interparticle structuring and behavior. And the other beautiful thing about small angle X-ray scattering versus, say, SLS is, since we have Q-dependent information, a lot of the information on clustering and interactions is encoded in the behavior as a function of Q. So for example, we can achieve sufficiently low Q in order to properly characterize the upturns that we believe are directly related to the formation of large networks in solution. With benchtop SAXS, improvements in the source, it is also possible to go even lower in Q range. So we are able to, with improvements in the equipment, can get to about 0.006 angstrom, inverse angstroms, which would get us effectively SLS levels of large length scales, which is a possibility in the benchtop. But for the systems that we studied, that has not been a requirement.
Wonderful.
Ask, what would you have to do, Amjad, if you wanted to take our current work down to 0.006? What would you have to change in your experiments? What would be the pros and cons of adding that additional range in your experiments?
Yeah, so the pros, there are theoretical pros that in that, if, for example, if there are so self-limiting clusters or intermediate range order that are of larger size than our range that we see here, then those, we could be missing those with the shorter range that we have taken. And so that could lead us to miss sort of self-limited clusters of a certain size. However, it is, structure factors that go down to about 0.005 inverse angstroms using both small angle neutron scattering and also synchrotron radiation are available in literature, and nobody in literature has seen these these interesting phenomena for antibodies at such long length scales. And so we believe that would not be a major concern. In terms
what
of
would you have to do? Let me ask you this.
Yeah.
Let's say you decided that you got a new monoclonal antibody and you were wondering what it might be doing at 0.005, and you wanted to get those data and to see what that might add. What would you have to do with your current experiments, and is that something you could do?
Yeah, so effectively what we would have to do is the way SAXS works is that you can vary the distance between the detector and the sample, and this distance determines how low of a Q you can get to. And so the instrument that we have now, the detector is on the railing in this tube, and we can push the detector even further, and we can theoretically get lower Q. However, since the scattered photons have to travel a further distance, you have a related increase in noise at those low Q regions. And so we have the capability to do these experiments, and we have done them in the past to get to even lower Q. However, to compensate for that, for the much higher noise that is observed at these longer detector distances, we have to run our experiments for much longer to collect the requisite amount of signal to noise ratio. An alternative that we could do is we could get a more powerful radiation source, which would then increase the intensity of the incident beam, which would also increase signal to noise. So it is possible, if we believe that the larger length scales have important information on clustering and viscosity, it is possible for us to do those, perform those experiments.
Well, doesn't it depend a lot on concentration? So if you're doing, 200 mg per mil, it gets easier, right? Or
it does,
250
yes.
mg per mil, the higher the concentration, obviously, the more scattering. So, 200 mg per mil, is that realizable now with our equipment?
At 200 mg per mil, with our equipment, we can get decent information at lower Q with measurements on the orders of a few hours. Yes.
Awesome. Okay, good. That's very addressable.
Awesome. Thank you both, and thanks for expanding on that. So we do have a few more questions. Another one came in. Amjad, do you believe that all highly viscous MABs are a result of clusters forming, and specifically greater than 100 CP at 150 milligrams per milliliter?
Right. So MAB behavior can be very variable, but most of the proteins that we have studied and that have also been studied in literature have shown a significant correlation, general correlation between the increase in attraction on the MABs and increase in viscosity. So I believe that the most common form of viscosity increase that we see in concentrated MAF solutions are likely due to the formation of these reversible clusters. There are, of course, other mechanisms for viscosity, increase in viscosity, specifically, if you weren't thinking about these very extreme cases of greater than 100 centipoise at 150 mg per mil, you could have native dimerization that could increase viscosity. You could have differences in the effective specific volume that the protein occupies based on repulsion or other interactions, or just the protein size that could affect the viscosity. So there are definitely other mechanisms that are possible, but we believe that especially...
For a second to your Jeremy Schmidt slide that you showed earlier. So following up on your question, how much do you think we know right now about protein clusters, the possibility of having, extended chains or proteins, and viscosity? Are we kind of early on in stages of this, do you think? Or do you think there's a lot to learn still, or do you think we're far along?
I think there's a lot to learn. I think there have been a number of studies that have shown correlations between interpreting viscosity data or simulation data to using models that introduce clustering and reversible oligomerization and comparing that to experimental viscosity data. However, I think what's still missing is a more direct experimental evidence of these, characterizing these clusters directly in solution and sort of building a mechanistic and not just purely correlational understanding between these clusters and viscosity. So,
well, given that we have a viscosity summit, let me ask you this. So with SAXS, you're learning a lot from SAXS about clusters. Tell us about studies of shear thinning and how you think that might give complementary information about clusters that's different than SAXS kind of gives you static measurements of clusters. Could you say a little bit about the differences and what those two techniques probe and how they may be complementary?
Yeah, absolutely. So, yeah, as you mentioned, SAXS would give us the sort of equilibrium state of the solution, including any irreversible clusters that may be formed based on molecules that are more likely to be next to each other due to intermolecular interactions. And that gives us the equilibrium picture. However, with shear rheology, specifically with shear relaxation, we can understand directly what length scales and interactions within species that are involved directly at determining the viscosity. And by characterizing the shear relaxation behavior, we can understand which species that we observe in our equilibrium state using SAXS may be more relevant towards determining dynamic behavior, such as viscosity. So I believe they're complementary in the way that SAXS can inform the equilibrium sort of zero shear condition and give us a range of the type of species present in solution. And shear rheology can help us identify, based on dynamical behavior, what characteristics of these clusters that are present in solution are relevant for dynamic viscosity behavior that we observe.
And, especially for some of these industrial MAVs, when they have significant concentrations, obviously the shear rheology to go to high shear rates takes higher flow rates through the capillary rheometer, but we have this. And so for many of these systems that are being investigated, the quantities are sufficient to be able to do high shear rates. And the nice thing about studying clusters through understanding these shear stresses and understanding how these clusters break at high shear rates is that it tells you something about the clusters that directly connects to viscosity. And after all, when you inject through a needle in subcutaneous injection, that involves very high shear rates. So to some extent, studying shear rate effects to understand clusters and rheology would be probably the most direct method to characterize clusters that are of great interest in a lot of practical scenarios. You know, in the past, sometimes we've had a high enough quantity of MABs to do shear thinning. In some cases, we've had, you know, very small amounts. And you know, if we go to just a single shear rate with the RheoSense, the nice thing about the RheoSense is there are two different ways to do it. And we can work with, what's the smallest quantity you could work with in the RheoSense with the, you know, with the adaptation kit that you know, ideas they have. So you can go from just incredibly small amounts. What would that amount be?
We can do it with, you know, as low as 20 microliters of proteins.
Okay. Okay. And then when we go to the shear thinning experiments, if we did go to, you know, really high shear thinning rates, then we, you know, we could need as much as what? 10 times that much? 100 times that much?
Yeah, easily 100 times as much if we go to higher shear rates.
Whereas the SAXS, you know, we can do with very small amounts. So I think that the strategy that we see is doing this RheoSense work at certain shear rates and learn about viscosity. Do the SAXS, do all this with small quantities, but then in cases where we have more protein, the shear rate experiments are extremely informative.
We're getting in a few more questions and only have a few minutes left, so I'm going to try to get to as many as we can.
Okay,
and
okay.
Any questions we don't get to, oh no, Dr. Johnston, I love everything you're adding. We're just getting them in now. Any questions we don't get to, I will actually send to our speakers and see if they can take a little time offline to answer, and then we can be sure to answer it after the presentation ends as well. But we did have a question. Have you tried any other traditional stabilizing agents like trehalose?
We have, yes. So what we showed here is just a very small subset of the different excipients or cosolutes that we've used. In the past, we have tried trehalose both as a lyoprotectant, as a stability, to improve stability, and also to decrease viscosity. And specifically, you know, I think its ability as a lyoprotectant and stabilizer is well known. In terms of decreasing viscosity, we've seen mixed results depending on the system we use, but that's something we've considered and will consider.
It usually doesn't lower viscosity very much, but to the extent it keeps the protein stable, that will, of course, help with viscosity.
Wonderful. And have you studied other rheological models, for instance, the Huggins equation?
We have, yes. So people in literature have studied quite a large number of models, including the Huggins equation. And I think as phenomenological models, most of them will give a decent agreement to behaviors. They work well as descriptive models, but very few has been shown to be predictive beyond certain levels. So getting Huggins coefficients at low concentrations and trying to relate them to high concentration viscosity has not shown very positive results.
You know, those models don't bring in clustering as Jeremy Schmidt's model does, as Ken Dill's model does, and our model does. So in that sense, all that gets kind of averaged out in those models.
And can this approach be adopted to protein therapeutic modalities other than MABs? Have you or others tried that?
Yeah, absolutely. So the approach we take is very general and can be adopted to any proteins. We have done work with polyclonal antibodies in the past versus monoclonal antibodies, which has been done with globular proteins, crystallins, and then in terms of in the therapeutic space, people have worked with short-chain variable fragments, FV fragments, bispecific antibodies, dual variable domains. In the pharmaceutical space specifically, you know, SAXS, understanding interactions and real clustering using SAXS can be, morphologies using SAXS can be used for drug nanoparticles and drug delivery vehicles as well. So the application for the technique is very broad, and we look forward to working with systems other than antibodies, and we already have some experience in that as well.
Wonderful. Well, we have a few other questions in the chat pane. However, we are just about out of time as our next presentation is beginning at 10. I would love to thank Amjad and Dr. Johnston for taking the time to be with us today and for sharing this amazing presentation and your research. It's been really just incredible to be able to learn from both of you, and we would love to continue to work with you. And if we have anyone interested in connecting with you, please let us know at RheoSense, and we would be happy to share your messages with Amjad and with Dr. Johnston and allow them the opportunity to connect with anyone. And as I had mentioned, if you did have a question that was dropped in the chat pane and we were not able to get to it, don't worry, it will not go unseen. We're going to go ahead and just kind of take those questions offline, and I'll be sending them directly to Amjad and to Dr. Johnston so they can look them over and help us to answer those and make sure they're all addressed. Again, it'll just be offline, but we, again, want to thank you both so much for taking the time to be with us today, for joining us on our first Viscosity Summit. And we want to just let everyone know, like I said, our next presentation is starting at 10, and we would love for you to join us, as our next presenter will be Bristol Myers Squibb scientist Barton Deer, and we would love to have you there. Thank you again.
Thank you for all of us together.
Dr. Keith
Thank
Johnston.
you. Thank you.
And with that, we're going to wrap up this recording and go ahead and get ready for our 10 a.m. presentation.
And as you're setting that up, all of this polymer rheology is going to be very useful to understand the monoclonal antibody rheology. So that community is really further along in rheology than the MAB world is.
Absolutely, absolutely. I'm going to go ahead and end the session, but thank you. And Amjad and Dr. Johnston, if you'd like to join us for any of our other presentations today, we'd love to have you on and have you see what else is there. Thank you.